All right, now let's check out what is conditional probability and independence. So by definition, conditional probability is a probability of an event given some other event has already occurred. And we show it with, mathematically, we show it by this equation. Probability of y given x is equal to probability y intersect x divided by probability of x. If this is the first time that you're staring at this formula, it doesn't make any sense at all. I totally get that. But I'm quite sure that you don't need to know this formula to give me the answer for the next exercise that I'm going to share with you. All of you guys intuitively know what is conditional probability. And if you think you don't know, just rethink it, because when I give you the example, you will for sure answer all the questions that I ask without knowing this formula. So bear with me. I go over the independence and I will open up that example. Now, how we define the independence? So we say two random variables are independent. Random variable y and x are independent if the probability of the intersect, y intersect x, is equal to the probability of y multiplied probability of x. Okay. And if I have this, then I can use this equation and plug it here and get to here, right? So remember, I can write it like this: probability, if two random variables are independent, then I can calculate the probability of y intersect x, so it's equal to probability of y multiplied probability of x divided by probability of x. I can cross out these two things because both of them are positive. Now I'll end up with probability of y. But what does this mean in simple language? So it says that if x and y are two independent random variables, then the knowledge of the value taken by x tells us nothing about the probability that y takes on various values and vice versa. In other words, it's really, the probability of y is independent of x. Regardless of what is the value of x, the probability of y is going to be the same if you look at different values of x. Okay. I know it sounds a little confusing, but let's look at an example. Let's work through an example, and all these things are going to make perfect sense, I'm quite sure. All right, so let's go back to an example. We are working with a very small, tiny data set here. And actually, I use two different colors. And imagine the variables of interest are y, capital Y is my random variable. Let's say it's wage, hourly wage. And capital X is gender. Okay. Later on in the course, we will argue that, okay, gender, it's not a good random variable, so you have to even call it male or female, make a dummy variable. So gender is not a good name. But again, for the sake of argument, let's say that our random variable is gender. And we only have two types of gender, male and female. Okay, we are just making some assumptions. Now, imagine I have 5 observations in this data set, and these are the numbers. So the observation number 1, it's a male, and then what is the wage? $20 per hour, right? Well, let me use another color because I'm going to color code whatever we say here. So let's say observation number 1, observation number 2, 3, 4. Oops, I can type 4 and 5, right? So the first guy is a male, wage $20 per hour. Second one, also a male, $25. Third one, female with $30 per hour. Fourth one, a male, $30. And finally, the last one is a female with $20 per hour, right? So the black ones are male, the red ones are female. Okay, so we color coded this way because you can see when I talk about a conditional probability based on gender, you can easily distinguish male versus female. Okay, now let me ask you a question. Imagine I ask you, what is the probability of wage is equal to 20? Remember, our wage, we show wage with y, given x is equal to male. Pause the video and think about it. I'm quite sure you're able to answer this question. Remember, what is the probability that we're interested in this question? What is the probability that the wage is equal to 20 and we're only looking at males? Without knowing anything about that formula that we used in the previous slide, So let's think about it. Let's think about it intuitively. Conditional on X is equal to gender is equal to male. So this means that let's narrow down the data to black observations, right? So only looking at those three black observations, 20, 25, 30. What is the probability, again, 20, I'm talking about, well, I'm going to erase it. So if I focus on the male only, I'm focusing only on these observations, right? I want you to look at these three observations and tell me what is the probability that wage is exactly equal to 20. How many outcomes I have? 3. What's the probability that is exactly 20? So it's 1 divided by 3, right? Because it can be 20, 25, 30. So what's the odd that it's exactly 20? The answer is 1/3. Does that make sense? So without knowing anything about the definition of probability, you were able to come up with this answer. Now let's go back and calculate this thing using the formula that we have here. Remember, probability of y given x is equal to probability of y intersect x divided by probability of x. Okay, so let's do it that way. I know, let me use another color. Probability of y is equal to 20 given x is equal to male. Using that formula is going to be equal to probability of y equals 20 intersect x is equal to male divided by probability of x is equal to male. I bet you can answer these questions as well. So what is the numerator? The probability of y is equal to 20 and x is equal to male. Remember, we're looking at all the observations now. And I have 5 observations, 5 outcomes, right? And then what is the probability that y is exactly equal, wage is exactly equal to 20 and x is male? So 20, I have two wages that are 20, this one and this one. How many of them are male? Just one of them. Okay, so what is the odd that out of these 5 observations, wage is 20 and gender is male? There you go, 1/5. Does that make sense? So that's the numerator. What about the denominator? What is the probability that out of these 5 guys, we're only focusing on the males. So how many males do I have? 3. What is the total number of outcome? 5. So 3 divided by 5. So this is a probability. Now, if you do the math, let me zoom out a little bit. If you do the math, 1/5 divided by 3/5, so the answer is 1/3. There you go. This is exactly the same as what you calculated up here, 1/3. So without knowing anything about the definition of conditional probability, you were able to calculate all these things behind the scene, right, in your mind. So that's. I hope you realize that it's not a complicated thing. If you only look at the formula, you think that, okay, what does it mean? Does it make sense? How does it work? But it's very intuitive. If you always think about this question, it's very intuitive. So conditional probability, your first job is to, what is that conditioning down variable? This means that narrow down the data set based on those conditional variables and then calculate the probabilities. That's simply it, right? Now that we know what is conditional probability, let's explore our first definition of independence, which is the strong independence. Remember, we have 3 types. Well, we have 3 types of independence. So the first one is a strong independence, which leads to weak independence, which leads to zero correlation. So these are different versions of independence. But usually in the statistics courses that you have taken, when people talk about this independence, they mean strong independence. So if you see independence, we mean strong independence. Okay. Now let's see what is a strong independence. And going back to continue with our example. So question number 1 that we are going to explore is X and Y independent. And remember, when I say independent, I mean independent. Oops. I cannot talk and type. Independent. We mean strong independent. So what was the definition of a strong independence? Mathematically was if the probability of y intersect x is equal to probability of y multiply probability of x. And or in other words, we say if the probability of y given x conditional on x has nothing to do with the value of x is going to be exactly equal to probability of y. Okay, so let's explore this one. Let's see in our simple example if the probability of y given x is equal to probability of y. Okay. All right, and we have to check it, guys. Remember, we have to check it for every single values of x. So here, what are the values of x? Male, female. Let's do it for one of them, and if it holds, we continue. We go ahead and check for the second one. But if it doesn't hold, we stop there. We say that okay, these two random variables are not independent, are not strongly independent. Okay. All right. So let's start with male or female or whatever. Let's start with male. So I'm trying to squeeze it in one page. You see the numbers up there as well. So probability, let's check again. The goal is to check if x and y are independent here, strongly independent. So probability of y given x is equal to male. Okay. And we want to see if this is equal to probability of y. Okay, and our y, so we should assign some numbers to our y as well. So let me go ahead and use another color. All right, so let's say we want to explore if we have to do it for all the observations of y. So let's start with y is equal to 20. So we have already calculated what is the probability of y is equal to 20 given male, right? So the answer was 1/3. We want to see if this is equal to probability of y is equal to 20. So basically, what is this? Probability of y is equal to 20, right? So what is the probability of y is equal to 20? Look at the table above. So what are the values of y? 20, 25, 30, 30, and 20. So I have 5 outcomes. How many of them are 20? 2. So what is the probability? 2, 5. Are these two numbers the same? No. So if the numbers are not the same for one of the values of your y variable, so you can go ahead and conclude that x and y are not independent. We're going to stick to this example and explore mean independence or weak independence and then zero correlation later on. But again, the first thing is strong independence, and we showed that these two random variables are not strongly independent. It means that the probability of wage given male is not equal to probability of wage, okay, for any values of those wages, 20, 25, 30, 30, and 20, right? Okay, so that's the first thing. We're going to go back and forth between this whiteboard and the slides multiple times. So we are clear with the first version of independence, strong independence. Let's move on to the next one. But for the next one, before going over the conditional expectation, well, mean independence or weak version of the independence, we have to clear some terminologies first. And that's the expected value and then median and some properties of these expected values, right? Because remember, the goal is to figure out what is expected value of y given x. We want to talk about conditional expectations. So I already know what is conditional probability, so this is done. So here's the question: what is a conditional expectation? Okay. But before that, we need to know what is expectation itself and what are the properties of expectation. So this is really straightforward. Most probably you guys are familiar what is the definition of expectation. So these are the measure of central tendencies. So for instance, expected value is a measure of central tendency and median is also a measure of central tendency. If x is a random variable, we show expected value of x is a summation of little x multiply the PDF of x. Remember, the PDF, we showed it with little f, and these are the probabilities, right? For a continuous random variable, we have to take the integral. So the integral of x and f of x. And I think it makes more sense to follow these things with a discrete version. And for the continuous version, we have to do integral, but we skip from those arguments, from those discussions. We're going to stick to the simple discrete version. Okay. Let's actually calculate one of them. Again, this is also one of those easy and intuitive terminologies, but if you want to think it mathematically, it makes you think, okay, it's a scary, but it is really not as scary. It's very simple. Let's look at the expected value of x, and imagine in our previous example, I'm looking at the expected value of x is a random variable, right? So I want to look at the expected value of wage. Okay. Without knowing anything about this formula, I want you to focus on this table and tell me what is the expected value of wage. What I have, I have 5 different wages. And what are the numbers? 20, 25, 30, 30, 20, right? So what is the expected value of wage? You're going to say that, okay, wait a minute, the data is symmetric. I have a couple of 20s, I have a couple of 30, and I have a 25 right in the middle. So the expected value is 25, right? So you calculated this one without knowing anything about the formula. But now let's open up this formula and see if we can get exactly to the 25 as well. So expected value of wage is a summation of wage I. Remember, I is a number of observation, is an index for the observation. It goes from 1 to 5. In that example, I have 5 observation. Multiply f of wage I, right? So going back to this, what is wage 1? 20. What is wage 2? 25. What is wage 3? 30. Wage 4? 30. Wage 5? 20, right? So the wage I is clear. Now, what we don't know is the probability of wage I. Remember, it seems that this is well, what is the probability that wage is equal to, or here, wage 1 is equal to 20. So we know that the answer is 2/5 because I have a couple of them. What is the probability that wage is equal to 25? It's 1/5. What is the probability that wage is equal to 30? It's 2/5 again, right? So I know the probabilities as well. All right. All right. So we know the WIs, we know the F of the WIs, which are the probabilities, right? Remember, for 20, it's 2/5. For 25, it's 1/5. For 30, it's 2/5, right? So let's do the math here. So it's going to be equal to, for 20, oh, sorry, guys, it just skips. For 20, it's 2/5 plus. For 25, I think we had one of them 1/5. And for 30, we had two of them 2/5, right? So I can factor these 5s and say, okay, 20 multiply 2 plus 25 multiply 1 plus 30 multiply 2. If you do the math, we will get to 25 again, right? So again, without knowing anything about this formula, you were able to calculate the expected value of wage, which it was 25, right? You might say, what is the difference between expected value and average, right? So can I simply take the average of these numbers and call it expected value? Expected value and average are the same, only the distribution is uniformly distributed, right? Only if, for instance, the probabilities of every single observation is the same as other ones. So for instance, it's 1/5, 1/5, 1/5, 1/5. And if that's the case, yes, average is exactly equal to expected value. But for many cases, the probabilities are not uniformly distributed, and the expected value is different than the average. Okay. Okay. So that's one thing. And for continuous random variable, we just the process is very like this one, but we have to do the integral, and because we have to calculate the areas and things like that, we don't do these things manually at all. I just wanted to show you a very simple example that we do it manually, and then you feel comfortable knowing these formulas, and then you can trust the outputs of R or any other kind of programming software. Okay, so that's the expected value. The second measure for central tendency is median. So we show median with little m, and it's a value such that one half of the area under the PDF is to the left and the other half is to the right, right? So if I have a continuous, I'll give you a continuous example here. Continuous random variable. So this is going to be my median. Half of the data is to the left of the PDF, half of the data is to the right of the PDF. If it is discrete, it's even easier. You just need to, if you have a bunch of numbers, so for instance, I don't know, I have, these are the numbers, let's say, -2, 3, -1, 0, 5, okay? So how do I know that what is a median? So your job is to first sort them, ascending or descending, really doesn't matter. Sort them and then count the number of values. So here we have 5. If it is odd, that's right in the middle. If it is even, you have to sum the out of the middle ones and divide it by 2, right? So here 0 is going to be my median. So this is the example for the discrete version. Again, so for continuous version, you just find the number that half of the area is to the left, half of the area is to the right. For discrete version, you sort the data and then you look at the observation right in the middle. So this is another example. Median is another example for measure of central tendency. And it's really straightforward, I believe. But what are some properties? So here and here. Median is less sensitive than average to extreme values or to outliers, okay? So this is again, very intuitive. For example, so the example for that is median income or median housing price. Which one do you think is a better measure for central tendency? Think about it. So when you're reporting the housing prices in the US, for example, should I look at the median housing price or average or mean housing price? The answer is median, right? Because as we just said, median is less sensitive to outliers. And when it comes to wages, when it comes to housing prices, there are some multi-billion dollars property, there are some multi-millionaire people that are going to skew the distribution. Okay, we're going to talk about the skewness in a minute. But it means that the mean, the average is not reliable anymore. So you have to look at the median for the central tendency of the data set, right? If you want me to give you another simple numerical example, and use another color. Imagine I'm talking about this, and I add another observation. I add 1,000 here, right? So these are the these are the values: -2, 3, -1, 0, 5, and then out of nowhere, there's this other observation which is 1,000, right? Let's see how it affects and let me first, again, for sake of argument, let me get rid of this 5 because I want to make sure that our median is the same, right? So if this is my new set of data, -2, -1, 0, 3, and 1,000, what is the median? Still 0. What is the mean or average? Average is crazily different, right? So it's -2, -1, +0, +3, +1,000, and then divided by 5, right? So it's 1,000 divided by 5, the average is going to be 200. But the average for the blue observations, look at the average for the blue observation. So the blue observations are the one with 5 instead of 1,000. What was it? It was -2, -1, +0, +3, +5 divided by 5. So this was 1. Look at that. 1 versus 200. So the average is super biased. Does that make sense? So that's why we say that median is less sensitive to outliers than the average. And it's a better representation of the central tendency in the data whenever the distribution is skewed, very skewed. And when I say skewed, it means that we have a bunch of outliers on either tail, left tail or right tail. Okay. However, I think this comes without saying, if X is symmetric, then the mean and median are exactly the same, right? Because if it is symmetric, it means that, so for instance, for the continuous version, it's easy to see, it's symmetric, and it doesn't need to be normal. It can be something like this, right? As long as it is symmetric, the average, mean, and median are the same. For the discrete version, symmetric means that, if we want to stick to that example, -2, -1, 0, 1, 2. So this is a symmetric example of symmetry. So the mean average and the median are going to be the same, which is equal to 0. All right. What are the other properties of expected value? And the first one, for any constant c, the expected value of a constant is constant. This makes perfect sense, right? So imagine your random variable is a constant. Your random variable only takes one value, and that number is 10. 10, 10, 10, 10, 10, 10. What is the expected value of this? 10. What is the average? 10, right? So this is one property. The second property, this is really important. For any constant a and b's or any constant can be positive, negative. The expected value of the ax plus b is equal to a expected value of x plus b. Okay. This means that, when you have a constant plus some random variable, then you can take out that constant from the expectation. Also, you can take that constant which was multiplied from the multiplication to the x, right? So this is a very important property that you're going to use. For your homework 3, you need this property as well. I think you need these two properties for homework 3. In this course, and by the way, I should have mentioned it earlier, guys. The materials that you're doing in this slide is non-testable. I'm not going to test you on your statistics because that's not my job. My job is to test you on your econometrics. However, in the econometrics, you need to know these materials. So I'm not going to directly ask you any questions from homework 3 on the exam, from homework 3 or the quizzes that I submit online or whatever you see on these slides. So these are non-testable. However, you need them for the rest of the course. Okay, so property number 3. It says that the expected value of a sum is equal to sum of expected value. This is a very nice property. So what do I mean? Expected value of a sum of a random variable. So for instance, x plus y is equal to sum of expected value of x plus expected value of y. And by the way, guys, you can use the definition of expected value here and use a method. You can mathematically prove this. But we don't prove anything in this class, or even if I do it, you're not I don't expect you to prove anything. Okay, this is an applied course. But for fun, you can give it a try. Try it home to prove it mathematically that the expected value of a sum is exactly equal to sum of expected values. Okay. All right. So this is one thing. Now let's move on to the next slide. Yep. I don't know why it doesn't. Okay. This is, okay, I didn't skip it. Okay, now we know what is the definition of expected value and the properties of expected value. Let's talk about the conditional expectation. Remember, we know what is conditional probability. Now it's time for learning what is conditional expectation. Okay. For conditional expectation, the formal definition, again, is one of these ugly formulas that you think that, okay, what does it mean? But if you go back to our example, I bet, again, you can calculate this by looking at that simple example. Okay, so let's give it a try and see if you can figure out what is this formula. So again, mathematically, expected value of y given x is equal to the summation of yi multiply f of y given x. And this is for the discrete version. You can imagine for the continuous version, of course, instead of summation, we have integral. Wait a minute. So let me. All right, now let's go back to our example and see if we can figure this out on our own. So let me make a separating line. We want to talk about the conditional expectation. So the first one was conditional probability. Let me write conditional probability here. Now we're going to explore conditional expectation. Conditional expectation. And imagine I ask you a question like this. What is the expected value of wage given we're only looking at males? This is conditional expectation, right? You want to calculate the expected value of some random variable given another random variable is fixed. So for instance, x is equal to male here, right? I want you to, pause the video and think about it. Look at the observations up there and tell me what is the expected value of y, given the fact that you're only narrowing down the data to males. Okay, pause the video and think about the answer. Okay, hope you got the answer. So if I condition the data based on only the black observations up there, so what is the expected value of wage? What are the wages for male? 20, 25, 30. What is the expected value? The average of that, right? So it's 25. When I say the average, because it's uniformly distributed here, the probability is going to be equal to expected value. But let's keep things simple. So you can see there's three simple numbers, 20, 25, and 30. What is the average? 25, right? So you knew nothing about the definition of conditional expectation, right? Now let's solve it with that definition. Expected value of y given x is equal to male is going to be equal to what? It's going to be equal to summation of y f of y given x. And remember, guys, what is this f of y given x? This is our friend conditional probability. We use this f and x interchangeably. But remember, as long as it is little f, you're talking about the PEFs. Condition here, this is a conditional probability, right? So let's figure out if we can solve this one, right? So again, I want you to pause the video and think about this one as well. This is a little bit more tricky, but you should be able to do that. All right, let's do it together. So let me zoom out a little bit, make sure that you see the table. I want you guys to focus on the black observations, only for the males, right? So we want to see, what is the summation? So what are the wages for the males? So it's 20 multiply f of y is equal to 20 given x is equal to male, right? You're only focusing on the male, plus 25 f of 25 given male, plus 30 f of 30 given male. Now, we're almost done, so we have to only calculate the conditional probabilities. So each of these things, we can use the intuition or the formula. Let's use the intuition because it's going to be faster here. What is the conditional probability of wages equal to 20, exactly equal to 20, and we're looking at males? 1/3, right? Look at that. Look at the three black observations. Only one of them is 20 out of 3. What is the conditional probability that wage is 25 and we're looking at males? Again, 1/3. And for 30 on male, again, 1/3. All right, so what do I have? I can factor in the 3's. So 20 plus 25 plus 30, what's the answer? 25. Okay, awesome. So I get exactly the same answer as what we did here, intuitively, right? The expected value, you're conditioning down to the data on only males and look at the average wage, right? All right, so now I know what is a conditional expectation. So when I know what is a conditional expectation, let's see if we can answer this question. We want to see if x and y are mean independent. Mean independent. I think it's really straightforward, right? We are talking about independency of their averages, mean independent. Mean independent. Okay. Sometimes we call it weak independence as well. Weak versus a strong independence. So here's our question. Okay, so let's go back and see what is the formal definition of mean independence, and we're trying to figure it out intuitively first and then go over the formula. So the definition of mean independence is this one. And guys, I want you to pay very good attention. This is going to stick with us for the entire semester, and I'm not kidding. So this mean independence is going to show up again and again and again. And honestly, this is one of the concepts that students have a little bit of difficulty absorbing it first. But if you stick with me in this example, hopefully you get a good grasp of it. But I want you to realize what is the definition of mean independence. So we say x and y, if x and y are independent, then expected value of y, and this should be mean independent. Sorry, my apologies. For mean independence, then expected value of y given x is exactly equal to expected value of y. Okay. What does this mean? This means that the expected value of y has nothing to do with the different levels of x, right? Remember, we say expected value. We never say that the value of y itself has nothing to do with x's. We say the expected value, expected value of y has nothing to do with x's, right? And do not confuse this guy with our strong independent, which was probability of y given x is equal to probability of y. So here we say that the probability of y is independent of x for every single value of y itself. Here we say the expected value of y is independent of x. So the average of all those y's are independent, right? So we're going to see that this is a weaker version. So this is a weaker version than the strong independence. All right, so let's go on the whiteboard and see if we can prove it intuitively. All right, so we want to see if expected value of y given x is equal to expected value of y. Let's see if that's the case. So, and you have to remember, guys, you have to check this condition, this statement, for all the values of x. Okay, so let's start with male. Expected value of y given male. I want to check if is equal to expected value of wage. So let's focus on the black observations, because remember, males were black on top of their in the table. So what is the expected value of wage given we're looking at males? We already calculated this one, right? It was 25. Is it equal to expected value of wage without any conditioning, down on? So when I say without any conditioning, what does it mean? It means that look at all the 5 observations up there, both male and female. So what is the average wage? So I have 20, 25, 30, 30, and 20. If you do the math, it's symmetric. I have a couple of 20s, 125 and a couple of 30s, so the answer is 25. So you can stop the video and do the math. So simply say, okay, 20 plus 25 plus 30 plus 30 plus 20 divided by 5, you'll see that the answer is 25. Good news. Okay, so I showed that the expected value of y given given male. So for male people, it's exactly equal to expected value of wage for all male and female. So can I conclude that, here's a question for you, that x and y are mean independent? The answer is not yet. Because remember, you have to check this statement for all the values of x. So let's condition everything down based on the female. I'm going to use a red marker because remember, our females, we show them with red numbers. So let's zoom out a little bit. Hopefully I can squeeze it in one page. Yeah, let's focus on the female observations. So let's use red here. Expected value of wage given female. We want to check if it is equal to expected value of wage. So what is the expected value of wage given female? Remember, how many females I have? 2. What are the wages? 30 and 25. What is the average between 30 and 20? Sorry. I have 2 observations for female, right? 1, 2. What are the wages? 30 and 20. What is the average? 25. What is the average wage? We already calculated for all the 5 observations, 25. Now, good news. I checked, so now we can say, yes. X and Y are mean independent. Mean independent. Okay, so I want you to sit back and stare at this one piece of whiteboard. What are we doing here? We are looking at a simple example. Very, very simple example, right? This one, only 5 observations. We showed that there are 2 random variables here, gender and wage. At the top part, we showed that gender and wage are not independent. It means that the probability of wage given X was not equal to probability of wage, right? However, even though they were not as strongly independent, we proved that in the bottom part, we proved that they are mean independent. It means that the average wage is independent of it's regardless of what is the gender. The average wage is the same as uh, the average wage in all the observations, right? So we can say the average of the wage is independent of gender. So this is a definition of mean independence. Again, guys, I really want you to pause the video and think about this mean independence a lot. Go back and forth between the slides and this whiteboard and make sure you understand it here, today, now, because I'm not kidding. We are going to look at this mean independence through the entire semester. And if you don't realize what is the subtlety with this definition, you're going to have a hard time understanding the basics of regression analysis. Okay. All right. So let me actually quickly go over these 2 properties, and we'll pause this video and make a third one. Okay, so what is the next property? The next property of the conditional expectation is that expected value of a function of x given x is equal to function of x. This exact same function of x. This is really, really straightforward. So let me give you an example. Let's say f of x, this is a function, is equal to x squared plus 3, right? I'm going to say that what is the expected value of this guy, f of x, given x, right? When I say given x, it means that fix the x and calculate the expectation for me. So if I fix the x is equal to 0, what is the answer? So x squared plus 3 given x is equal to 0. So what does it mean? It means that 0 to the power of 2, 0, and plus 3, 3. If x is equal to 1, so 1 squared plus 3, 4. If x is equal to 2, 2 squared, 4 plus 3, 7. So this is exactly the same as x squared plus 3, because we are fixing x. When you're fixing x, that conditioning thing doesn't, the average doesn't make any sense. That's exactly as if you're plugging it to the function. So this is f of x. Okay, so this is an important property. I hope that you get the idea. When you're conditioning down based on the variable itself, the expected is going to be the same as the function of x, exact same function of x. All right, and finally, with this property, we can get to the property number 3 for 2 different functions, f of x and g of x. These are 2 different functions of x. The expected value of f of xy plus g of x given x is equal to what? So as long as there is x in any of these functions, we know that the expected value is the same as the function itself. So we can take out that function, which is a constant now. Remember, you're fixing x. If I fix x, the expected value is going to be the same. Do you remember in the previous slide, the properties of expected value of a constant is a constant? This is exactly what we're doing. Expected value of a function of x, given x, it means that fix the x. So expected value of a constant is equal to a constant. It's equal to f of x, right? So it's going to be equal to f of x, expected value of y given x. However, you cannot take this thing out because this is still y given x. So you have to make sure that you write it like this. So it's going to be equal to f of x, expected value of y given x, plus g of x, because there's an x here, there's an x here, it's constant, we can take it out, okay? All right, so these are the properties that you should know with respect to what is conditional expectation and what are the properties. So let's go to the next slide. and pause the video here.